Hello there, this is Jude Socrates. Welcome to today's video where we are going to do some integrals that have trigonometric functions. So we know the basic formulas. We know that the integral of cosine is sine, the integral of sine is negative cosine, but what happens when you put these functions together? So these are the kinds of integrals that we are going to learn about today. What happens when you have powers of sine combined with powers of cosine multiplied together in the same integral? And analogously, what happens when you have powers of tangent combined with powers of secant in the same integral? Now, we saw in the past when we did integration by parts that we know how to find the integral of a pure power of sine. We have a reduction formula for that. And of course, there's a corresponding one for cosine. So similarly, you can have pure powers of tangent and secant in the same integral. Okay, for example, what is the integral of secant squared? We know that that is just tangent. So what happens if you change the power? We're going to see how to integrate secant all by itself and secant cubed. Same thing with tangent. Hopefully you remember how to integrate tangent. It involves the ln, but we will review it in a little bit. But more generally, what happens if you have powers of tangent multiplied by powers of secant? We're going to do some of those. All right, so as you can imagine, very often we're going to need the basic Pythagorean identities in order to find these trigonometric integrals. So everyone should know that cosine squared plus sine squared equals 1, always, for any angle theta. And if you divide both sides of this equation by cosine squared becomes 1. Sine squared over cosine squared is tangent squared. 1 over cosine squared is secant squared. So this is the corresponding Pythagorean identity that involves tangent and secant. Now, in a little bit, we're going to see that when the power of sine and cosine are both even, we will need the double angle formula for cosine, and correspondingly we will get formulas for cosine squared and sine squared. Okay, so the basic formula that I like to remember, very easy to memorize, is that cosine of 2 theta is cosine squared theta minus sine squared theta. We are going to convert this formula into a pure power or expression involving only sine or cosine by using the Pythagorean identity. Cosine squared is 1 minus sine squared. So subtracting another sine squared, we get twice, 1 minus twice sine squared theta. Similarly, if we replace sine squared by 1 minus cosine squared, this one's a little trickier. Distribute the minus 1, the minus, so we get a minus 1, and we get the plus cosine squared, so we get 2 cosine squared theta. Okay, so from here, we have 2 formulas. We can isolate sine squared as well as cosine squared. Let's start with cosine squared. Move the minus 1 over to the left side, so we get 1 plus cosine 2 theta of 2 theta divided by 2, because there's a 2 over there. Okay, now for sine squared. Since it has the minus sign, let's move it over to the left side where it becomes plus 2 sine squared. And let's move the cosine to the other side where it becomes minus cosine 2 theta. Okay, if you don't believe me, do the algebra yourself. And then we divide both sides by 2. So basically, we get exactly the same thing, except instead of a plus, we get a minus. So I will just do that. And there we have formulas for cosine squared and sine squared. All right, time for us to get to work. We want to find the definite integral from 0 to pi over 4 of sine squared x cosine cubed x dx. So this is a combination of powers of sine and cosine. And this is the easy case where one of the powers, either sine or cosine, doesn't matter which one of those powers is odd. So in this case, that's the 3 that you have over here. So when that happens, we can actually do this by a simple u substitution. So in fact, you could have seen this in your final exam in Calculus 1, first semester calculus. So all we have to do is borrow one of the cosines from cosine cubed. So what does that mean? Copy the problem. We are going to change cosine cubed to cosine squared, and we are going to peel off one of the cosines. Okay? So we have cosine squared cosine, back to cosine cubed. Okay. Why is this a good idea? I said it's just a u substitution. So who is the function whose derivative is cosine? That will be our u substitution. I hope you know that that should be sine of x. Okay, so u is sine of x, so du is cosine x dx. Okay, so that takes care of the du over here. Okay, let me complete the sentence. Let u be sine x, so du is cosine x dx. Okay, so sine squared is just u squared. Okay, we do have a problem with cosine squared, but it's not a big problem. So cosine squared, not power reduction, but just Pythagorean identity. Cosine squared is 1 minus sine squared. So because our u is sine of x, it is just 1 minus u squared. Okay? So yeah, this explains two things we're going to do. Sine squared is u squared. Cosine squared is 1 minus u squared. Excellent. So now, shall we change the limits? Okay, why not? Get some more space here. When x is 0, what is sine of 0? That's also 0. U equals 0. And when x is pi over 4, our upper limit, what is sine of pi over 4? I hope you remember. U is radical 2 over 2. Where's my radical? Here's a radical. And we have a radical 2 over 2. Or if you like, 1 over radical 2. Same thing. Okay, so now we are ready to plug in our substitutions. So we're here. And now we transform that. Pi over 4 now becomes radical 2 over 2. So we will copy that up here. The 0 is still 0. Sine squared x is u squared. So goodbye. And goodbye. Cosine squared, though, is 1 minus u squared. So I will erase this, and I will put 1 minus u squared in there. Cosine x dx, we said that that is our du. Goodbye, but dx is now du. Okay? So that package, cosine x dx, that is our du. Okay? You don't just change the dx into a du because it's inconvenient. Okay? You have to make sure it comes with the right factors or whatnot. Okay, so this is now a simple application of the power rule for antiderivatives, except we should distribute this a little bit. Okay, so maybe we'll just continue on the same line. We will distribute the u squared, so 1 becomes u squared, and u squared times u squared is u to the 4th power. Okay, there we go. So now that is integrable. We will get by the power rule. So I need a fraction. U squared becomes u cubed over 3. And u to the 4th becomes u to the 5 over 5. So let me make a copy here. U to the 5 over 5. And we're evaluating from 0 to radical 2 over 2. Okay, so let's put that up here. And we just have to plug that in. Okay, let's do this. 0, of course, goes away. We are cubing radical 2 over 2 and also raising it to the 5th power. But those are odd powers, okay? So the square root is not going to completely go away. So here's what I'm going to do. To keep it simple, I am going to take out one of the radical 2 over 2's. Okay, so I'll take it out. And now I have a square here divided by 3, okay, because I borrowed one of the u's, okay? So when you square radical 2 over 2, that should now be a 2. We're going to erase all of that. Square it, we just get 2 over 4, or simply 1/2. Okay? So similarly, for the u to the 5 over 5, that's down to a u to the 4 over 5. Okay? So 4th power is the square of the 2nd power, so we're going to get 1/4. Okay, isn't that a lot nicer than cubing radical 2 over 2 or raising it to the 5th power? Okay, little tricks that I like to do that makes life a little bit nicer to look at. Okay, 1/2 divided by 3 is 1/6, and 1/4 over 5 is 1 over 20. Okay, so yeah, between 6 and 20, the LCD, I believe, is 60. 20 times 3, 6 times 10. So let's clean up that fraction. So 6 times 10, you get 10 over 60. And then 20 times 3, 3 over 60. Okay, so that is 7 divided by 60. 60 multiplied by 2 is 120. So our final answer is 7 radical 2 divided by 120. And I did make sure that Maple agrees with us. That is the answer that Maple also got. Okay. So it's easy when one of the powers of sine or cosine is odd, but what happens when both of them are even, like we have in our next example? When that happens, use the power reduction formulas that we derived a little earlier. So, what are we going to do? We are going to change cosine squared to 1 plus cosine 2x. But we have a sine to the 4th power here, though. So we will have to square sine squared x. Okay? So let's do this. Let's do this. Copy and paste. So it's not quite a u substitution. It's basically just using identities. Cosine squared, we will use this, but it should be an x. Cosine squared is 1 plus cosine 2x over 2. But sine to the 4th is the square of sine squared of x. So we will square this. Sine squared is 1 minus cosine 2x divided by 2. So maybe to make it look nice, let's put brackets here as well. Okay, so that's great. Next, okay, so we don't need that anymore. I'll just let it scoot down and we don't have to look at it for a while. Let us expand this square. Okay, so trigonometry, algebra, all of that is important. Squaring a binomial a minus b quantity squared, a squared minus 2ab plus b squared. Okay, so a squared, 1 squared is just 1. And then minus 2ab, so minus 2 cosine 2x. I'm going to borrow this. But we'll have plus cosine 2x squared. So I'm going to bracket that and square it. Sometimes we just write cosine squared 2x, okay, just like I did over here. But because we're doing some tricky algebra, I want you all to see just exactly how the powers are, what are happening to those powers. 2 squared is 4. Okay, so we have a 1/4 and a 1/2. Let's take out that fraction as 1/8. Okay, so that way we have a shorter line to deal with. Okay, so this is just a convenience step. Take out the 1/8. So this is now what will remain, and this is what will remain. Okay, goodbye to the 4 and to the 2. So now we are going to distribute these two factors. Okay, I said this is the harder case. So there's going to be some distribution, some algebra to do. Okay, so to be organized, yeah, you know what? Let's do this. Let's do this. There are 3 terms here, but there are only 2 terms here. So what we can do is, we can take the first triple, multiply it by 1, which means nothing happens to it, stays the same. But we can take those same 3 numbers and multiply now by cosine 2x. Okay, we're okay with that? We're distributing these 3 terms to these 2. So first, the 3 all get multiplied by 1, which means we get these 3 terms. And then the same 3 get multiplied by cosine 2x. So we get these 3 terms. So now, let's simplify this as much as we can. Nothing happens to these first 3 terms. So we'll just take that, and we don't need the brackets. Now we distribute cosine 2x to these 3. So we have a cosine 2x. And then we have a minus 2 cosine 2x squared. So we are going to take that and square it. Okay, so remember, I'm doing this so that we can see what the real powers are clearly because of the brackets. We now see that there are 2 terms that have cosine squared 2x. So lastly, we have plus cosine squared, cosine 2x squared times another cosine 2x. That is now cubed. There we go. So let's put an equal sign. So those are the same. So now we can clean that up. We have minus 2 plus 1. So that's going to be a minus 1. And yeah, let's just copy that whole thing. So minus 2 and plus 1 now becomes a minus 1. So we can erase this. We have a plus squared and a minus 2 squared, so that becomes minus 1. And we can erase this. Okay, so this is what is inside the integral. And of course, we are going to integrate it one by one, term by term. Easy, use substitution. Okay, so we have cosine squared 2x, power reduction one more time. What about the cubed? Well, 3 is odd. Okay, so remember, when the power is odd, borrow one of the factors. And so we're going to get cosine squared left over. That sort of happened to our previous example, right? We borrowed the cosine, and we still had the cosine squared left, which we convert to 1 minus sine squared. Okay, we have the strategy. that is the strategy. So let us look at those formulas, those beautiful formulas again. And maybe let's get rid of this because this is not what we are going to integrate. Okay. So for those who are studying computer science, it's like doing a subroutine. Okay, so let's get the algebra and the trig out of the way first. Leave alone, cosine squared 2x. We'll need cosine squared theta, but this time theta is 2x. So if theta is 2x, 2 theta is 4x. All right, so that is very, very important. So the square the square goes away. And when you square, it becomes 1 plus cosine 4x. Not 2x, but 4x. And that's the reason why I used theta in these formulas instead of x. Okay, maybe you were wondering. But for the cubed, we will borrow one of the cosines. So that is now just a 2. And we have that. Okay, awesome. Now, maybe, I think it would be a good idea to simplify this further, because we like simplified things, don't we? So minus, and looks like we have a 1/2 there, so I will borrow this fraction. So that's going to be a 1/2. And the second term becomes minus 1/2 cosine of 4x. So minus 1/2 cosine 4x. I will erase this. That goes away. Quick check. Minus 1/2 cosine 4x. Okay, so this is now ready to integrate, but we have 1 minus 1/2. That's nice. So let's simplify further. So it's really simplified. 1 minus 1/2 is just 1/2. So that 1 becomes 1/2. Okay, and I do believe that these are now ready to integrate term by term. Okay, there is definitely value in simplifying an integral as much as possible before you do the integration. Okay, so this is where we left off. We can now return from our subroutine. Oops, sorry about that. All right, cut and paste fail. So I have pasted that whole thing inside, and we are now ready to integrate term by term. Okay, so let's just label. So the integral we want is now this thing. Okay, so we will integrate one at a time. There will be 4 pieces. And shall we keep the one? Yeah, let's keep the 1/8 outside. Bracket. So we have 0 to pi over 3 dx. Oh, and there will be 4 of them. Okay. So it's going to be plus, minus, minus, plus. Okay. So minus, minus, plus. Let's make 4 copies of this. Put it together. Okay. So the first one is simply 1/2. Second one is cosine 2x by itself. The next one is cosine 4x minus 1/2 cosine 4x. And the last one with the borrowed cosine 2x right there. Okay. So we can, well, why don't we take the 1/2 outside? These are easy to integrate, but we need a small u substitution. Okay, u is 2x. Okay, so for second, u is 2x. So du is 2dx. And dx is du over 2. 1/2 du. Shall we change the limits? So we're going to get 0 to 2 pi over 3. So for the second one, it's of course exactly the same, except 2 becomes 4. So dx will be du over 4. For the last one, we're going to use for our u not 2x, but cosine 2x. So that will be u squared. Oh, I'm sorry. No. We will, erase completely my suggestion, because we need something whose differential is cosine 2x. Okay, so that will be sine of 2x. So for the fourth, u will be sine 2x. So du is 2 cosine 2x dx. All right. And cosine squared, cosine 2x squared, is 1 minus sine of 2x squared. So let's put that step in. We need sine of 2x squared let's put the square outside. So that is our 1 minus u squared. All right. So I believe we are ready to plug that all in. We have used the double angle formula. So let's copy this whole thing. Start integrating. So we have 1/2 x evaluated from 0 to pi over 3. So we get 1/2 times pi over 3. That's just pi over 6. For the second one, we have a u substitution. So yeah, let's do that first. So cosine 2x is cosine u, and dx is 1/2 du. One-half d. Similarly for cosine 4x, okay, so I did not have a separate line there, so let's do it mentally. Okay, u is now 4x, so pi over 3 becomes 4 pi over 3. We're going around the circle. Cosine 4x now becomes cosine, let's call it v, because it's a different substitution. And then for the last one, dx is 1/4 dv. Okay, well, silly me, I used the same letter here, but that's okay, you're smart people. So cosine squared becomes 1 minus u squared. So we erase this. Just think of each integral separately. And the cosine 2x dx is, oh, we didn't isolate it, 1/2 du. So we take this out, 1/2 du. Okay, and shall we change the limit? Okay, when x is pi over 3, sine of 2 pi over 3. Okay, 2 pi over 3, we're in the second quadrant, and the sine is radical 3 over 2. Okay, so you need a radical. Okay, here we go. Clean that up a little bit. Radical 3 over 2. Quick check, our u is sine 2x. So 0, sine of 0 stays 0. There are some integrals, let me warn you. If your u is cosine, cosine 2x, cosine 0 is not 0, it's 1. Okay, that's one of the easiest places where you can make a bad mistake. Okay, so we are now ready to integrate second, third, and fourth terms. Okay, you have 1/2 on the outside. Integral of cosine is sine, so we have sine of 2u. Let's bracket that, sine of 2u. And we are integrating from 0 to 2 pi over 3. Okay, let's make sure we got everything. 1/2 goes outside. Integral of cosine is positive sine. I'm sorry. It's just sine of u. Take the 1/4 out, we get minus 1/8. And integral of cosine is again sine, so we get sine of v. And we're integrating from 0 to 4 pi over 3. Okay. Last one, we have 1/2. And we are in u, so we have u minus u cubed over 3. A fraction. U cubed over 3. From 0 to radical 3 over 2. Whoops. Clumsy fingers. Okay, so let's do a quick check here. So 1/2 dx, that just integrates to 1/2 x from 0 to pi over 3 is pi over 6. We have minus cosine u du. So this is the part that I really want to make sure we did it right. 1/2 goes out. Integral of cosine is positive sine, so the minus stays minus. Sine of u from 0 to 2 pi over 3. Take the 1/4 out, we have 1/8. Now we have sine of v from 0 to pi over 3. Take the 1/2 out, integrate, 1 becomes u, minus u squared becomes minus u cubed over 3, from 0 to radical 3 over 2. So now, we will plug in the numbers. Sine of 2 pi over 3, we did that a little earlier. Radical 3 over 2. Ooh, so radical 3 over 2 is going to appear a few times. Let's put a fraction down here. And we have radical 3 over 2. Sine of 0 is 0. So that takes care of our first term. But wait, there's more. Now we have sine of 4 pi over 3. We're now in the third quadrant. And sine is now negative in the third quadrant. So we have negative radical 3 over 2. So that takes care of this. Next, remember what we did earlier? We have an odd power. So let's borrow one of them, one of the u's, to make it cleaner. So this u now becomes 1, and this u cubed becomes u squared. U squared divided by 3. So we have u squared will be 3/4 divided by 3 makes 1/4. Ooh, exciting. So this is now 1/4. We have evaluated the limits at 0. Everything is 0. It's all good. Okay, we're getting close to the finish line. Start simplifying. We have radical 3/4 minus. We have a plus radical 3/16. We have 3/4 here and another 4, so 3/16 positive. Oops, my fingers are so clumsy. Scrolling away. Ooh, check it out. So now we have 3 plus 1, 4/16. That is 1/4 radical 3. We have a minus 1/4 radical 3. Awesomeness. So now all that remains is the pi/6. Woohoo! So our final answer is pi/48. Yay! And that is also the answer that Maple gave me. And if you don't believe me, that's okay. You don't have to believe everything that I say. Okay, I'm moving my cursor to the icon that says equal in Maple. It's right here in this corner. Woohoo! Pi/48. I win. We are now ready for the second part of this video, where instead of sine and cosine, we have powers of tangent and secant, or these two functions by themselves. Unfortunately, there are no rules where if one power is odd, borrow one, because we don't have those rules because of the somewhat strange derivative formulas. The derivative of tangent is secant squared, so you need 2 of the secants, but the derivative of secant is secant tangent, so you will have 1 each of the secant and tangent. And these two formulas might allow, not all the time, might allow a good u substitution. Okay, so if you can somehow borrow a secant squared x, the dx with the dx, then maybe tangent of x would be a good idea. Okay, you might have to try both first, to make sure, okay, which one, make up your mind, which one am I going to use? Remember the Pythagorean identities. So 1 plus tangent squared is secant squared. That might be useful. I'm not saying it is, but it could be. You could try integration by parts. We're going to do it for one of the problems below. So remember the integration by parts formula, where if you have integral of u dv, you solve for v, you solve for du, you put together u times v minus integral of v du. And you keep your fingers and your toes crossed that this second integral is easier than the first integral, or maybe just as hard. Okay, let's go. First problem is a review. Do you remember how to integrate the tangent function, tangent of x dx? Would you like to think about it for a second? Got it? If you did not, let's do it. So tangent is sine over cosine. And now we need a u substitution. Remember that part? So let u be, should it be sine or cosine? Well, remember we need a du, okay? And the du is always in the numerator, not in the denominator. So it looks like u should be cosine of x. So du is minus sine of x dx. There's a minus sign. So our denominator is our u, but sine x dx is negative du. So I'm going to erase that, and I'll put a minus 1 up here, minus 1 du. Okay, and you know which formula to use, right? So this is negative ln of the absolute value. Let me pause a minute. All right, I always have to dig up the absolute value bars from Maple here. Okay, so that is just negative ln of the absolute value of u. Where did u come from? So u is cosine x, so negative ln of cosine x. And for the coup de grace, we're going to put the negative sign inside the logarithm. We're going to use one of the power rules. So that's negative 1. So negative 1 goes as a power for cosine x. There it is. Okay? And of course, in this context, negative 1 power is a reciprocal. So it is negative ln of reciprocal 1 over cosine of x. So let me borrow this fraction here. But it is positive 1 over cosine x. And what is a shorter way to write 1 over cosine x? It is the ln of x. Okay, so, I'm sorry, I was thinking of the ln. It is secant of x. So, ln of secant of x. All right, so that is our formula for derivative of tangent. Now everyone remembers. It is the ln of secant x. Plus c, of course. Next level, tangent squared. Maybe we should turn that into sine squared over cosine squared. Okay, is that going to help? Well, if our u is cosine, then yeah, we have u squared in the denominator. If we have sine squared, we have too many sines in the numerator, and if you want, you need that extra sine of x, but you have, how do you get that from cosine 1? Blech, yuck. Okay, so that is not the way to do it. However, we have more tools, okay? Remember the Pythagorean identities. We have tangent squared. 1 plus tangent squared equals secant squared. So therefore, tangent squared is secant squared minus 1. And that helps because we know how to integrate secant squared. So now that we are getting deeper into integration, you probably noticed that sometimes what you try doesn't work. And that's life. That's calculus for you. Integration is much harder than differentiation. And it's not always clear that you have an end game, that what you're trying is going to lead to a happily ever after. Okay, so in this case, 1 plus tangent squared is secant squared. So tangent squared is secant squared minus 1. And we will just break that up. So of course we get just integral of dx minus integral of secant squared dx. Okay, dx, integral of dx just becomes x. Integral of secant squared is tangent x, because the derivative of tangent is secant squared. So we get x minus tangent x plus c. That is our antiderivative for tangent squared. Okay, we know how to integrate secant squared, but we don't have a formula for just secant by itself, by its lonesome. So how would we integrate secant of x? Now, this is one of those problems where if you were stuck on a desert island and had nothing better to do, and you forgot, and you took calculus, but you forgot how to integrate secant of x, you might spend a lot of time figuring out a way to do it, and well, you're stuck on a desert island, so there's not much left to do anyway, so might as well keep trying. But of course, we don't have forever. The video is already 45 minutes. So what do we do? Secant. So here's the trick. We need a trick. It's sort of like rationalizing. We're going to multiply and divide by the same thing. In this case, that same thing is secant plus tangent. Why is this a good idea? Because if we distribute the secant that we have with secant plus tangent, we get secant squared plus secant tangent. And those should sound familiar. So we don't just multiply, of course, we multiply and divide. Okay, so it's a lot like rationalizing. So we need an equal sign there. We will distribute that secant to our numerator. So erase, and this becomes secant times tangent, and the first becomes secant squared. So this time I'm not going to put brackets outside and squared, because what we're doing is relatively simple. Okay, so we see this now. Why is this good? Because the derivative of secant is secant tangent, and the derivative of tangent is secant squared, right? So if we let u be the denominator, secant plus tangent, then du will be secant tangent plus secant squared. So we already have our secant here, secant tangent, plus secant squared dx, which is the numerator, only it's in the different reverse order. Who cares? It's commutative. So we have integral of 1 over u du. Yay! So clean. So once again, it is ln of absolute value. Here I go again. All right, antiderivative of 1 over u is ln of absolute value of u. And our u is this. So final answer is going to be ln of absolute value of secant x plus tangent x. So that's not a pleasant looking formula, but it is what it is. And it's going to be very useful in some of the definite integrals that we are going to do next couple of videos over. So that's going to be one of our highlights for this video. So we're going to do a couple of examples where there are actual powers of both tangent and secant in the same integral. So when that happens, again, there are no fast rules to follow. Try to use substitution, integration by parts, whatnot, okay? We have 4 tangents, we have 4 secants as well. So this even power, that's good because the derivative of tangent is secant squared. So we have 4 of these. You have 2 for the derivative, and then you keep another secant squared. But we just saw that 1 plus tangent squared is secant squared. So it looks like the strategy is to make tangent x the u, and that will take care of the secant of the fourth. Let u be tangent of x. So du is secant squared x dx, and secant squared by itself. Okay, so it is 1 plus tangent squared. I always have to think a second, like which one is it? Is it a plus, minus? And tangent squared, so that is 1 plus u squared. Those are our ingredients. So we can plug this in now. We start with fourth power, but we break this up into two pairs. Secant squared and another secant squared. Plug in our substitutions. Tangent to the fourth. Well, tangent is our u, so that first factor is just u to the fourth. And erase. The secant squared is our 1 plus u squared, and this secant squared dx is our du. Okay, so they're different accounting. The first secant squared is 1 plus u squared, and the second one is du. There you go. That works because we have the power rule. But first we distribute. Something similar happened for the sine example. You remember? You don't remember? Back up. So u to the fourth, 4 plus 2, u to the sixth. Yay. So we get fractions, u to the 5 over 5. And u to the 7 over 7. And bring back our u. U is tangent of x. So it's just tangent of x to the fifth power. Tangent to the seventh power. There you go. So one thing about these trig integrals is that you might get an answer which is different from the answer in the answer key. And that might be because you did a different substitution, which might also work. Okay, so unfortunately, yeah, keep that in mind when you check your answer. How about this one? Definite integral. 0 to pi over 6 tangent cubed 2x secant 2x dx. So is tangent gonna work? You need secant squared for tangent, so that might be a giveaway that no, maybe that's not what will work. So let's try secant. So let u be secant of 2x, not of just x. So du is 2 secant 2x tangent 2x dx. Now, is that a good idea? Well, we have 1 secant 2x. That'll go with the dx. We're missing a tangent 2x. We can get one from cubed because there are 3 of them. But are we going to have an endgame? If we borrow one of the tangents, we're left with tangent squared. But we know that 1 plus tangent squared is secant squared. So we will also need tangent squared 2x is 1 plus tangent squared is secant squared, so secant squared 2x minus 1, which is u squared minus 1. Those are our ingredients. Now let's put the cake together. Cake. Oh, we still have our limits. Ooh. Remember how I warned you that, check it out. When x is 0, u is secant of 0. Is that 0? No, that's not 0. 1 over cosine 0. Cosine 0 is 1. And when x is pi over 6, u is secant of twice, so pi over 3. which is 1 over cosine pi over 3. Are you thinking? Cosine pi over 3, cosine 1/2, 1 over 1/2, so we get 2. All right, so we ready? 0 becomes 1, not 0. Pi over 6 becomes 2. And, oh, you know what? Let's do this. Okay, so first let's borrow the tangent. So we said that we are left with tangent squared, and we have tangent to x by itself. Okay, so that appears here, but there is a 2. Okay, so this becomes du over 2. Now we're ready. Replace the limits. Tangent squared becomes u squared minus 1. So yeah, there we go. U squared minus 1. And secant tangent dx becomes 1/2 du. Whew, okay, so we are ready to integrate. Oh my, if you listen carefully, you might hear really strong rain pounding on my roof, because this is the day when we got that cyclone bomb or whatever from the Arctic. Ooh, concentrate. U squared becomes u cubed over 3. And minus 1 becomes minus u. Okay, we want to evaluate from 1 to 2. All right, so we get u cubed, so 2 cubed is 8, and then minus 1. U is 2 minus 1. You get 2 minus 1. So that is just 1. So I think we got our final answer. 1/2. And we get 7/3. And then minus another 3. So that is 4/3. 4/3 times 1/2. I believe we get 2/3. All right, and that is our definite integral. For our final example, while it's pouring outside, we know how to integrate secant squared, and then we drop down to secant, just 1 power. And now we want secant cubed. And this integral is going to be very important, just like secant, for the next couple of videos. What are we going to do here? Integration by parts. We need a u and a dv. Okay, well, we got secant cubed. So can we integrate secant? Well, we just did, but it's not quite fun, right? But we know how to integrate secant squared. So perhaps that should be the du. It is. So du will be secant squared x dx, and our v will be a single secant x. Okay, so we got all 3. 2 plus 1, we get 3. Okay, so integration by parts formula. Okay, so remember, integral of v du is v times u minus integral of u dv. Okay, I may have switched the letters there, but that's okay. They are interchangeable. So we get this must be u, we need u and v, okay? So u will be tangent of x, the derivative of tangent is secant squared, and dv will be secant of x dx. I'm sorry, secant x tangent x. Woohoo! Bad mistake. Secant times tangent. Okay. So we need u times v. Ooh, u times v is secant times tangent. How convenient. So that's here. Minus integral of vd, well, I should watch my letters. Minus integral of the product of these two. U dv in this case. Okay. So we need dv in here. Take all of the letters. But we're multiplying by a tangent of x. Okay. So we have an extra tangent. So that will be a tangent squared x. Does that look better or worse than the original? Well, technically it's still third power. Okay, you got 2 plus 1. So it's not that better or worse. However, we still need to integrate that. So what are we going to do? One more time. Tangent squared. 1 plus tangent squared is secant squared, so tangent squared is secant squared minus 1. Secant squared of x minus 1. And that's good because, oh no, we're back to where we started, secant cubed. Ooh, remember when we did integration by parts? And sometimes you end up back where you started. It does not mean you just wasted the last 10 minutes of your life. You can probably, you might be able to solve for the integral by doing some algebra. Okay, so distribute. Secant squared becomes secant cubed. And we still have a minus secant of x. Okay, so now we split it up. We have secant tangent minus integral of secant cubed. And yeah, we're back where we started. So I'm going to copy that. But we have a minus minus plus integral of just secant x. So plus secant x, that 3 should be, oh wait, okay. So minus integral secant cubed plus integral of secant by itself. Okay, so bring the minus secant cubed over to the left side to join the original integral of secant cubed. Algebra. So I'm going to put our work so far. Okay, this becomes the minus here goes over to the left as a plus. Remove that. You remember what this was? Well, fortunately, we are going to summarize that. So I already put that over here. Haha, there it is. Why do I have 2 equals? Secant is ln secant plus tangent. And we have room for the one we're working on. Okay, so let's put that on the next line. On the left, there are 2 of them, so that becomes 2. 2 integral of secant cubed. Make sure we got everything. There are 2 of them now. Secant tangent is still there. We know that the integral of secant is ln of secant plus tangent. Okay. So now, we can divide by 2. And so multiply by 1/2. All right, 1/2. And we have this secant tangent plus ln of secant plus tangent. Okay, so this is a little bit of a tricky formula because here secant and tangent are multiplied together, but over here they're added together inside the ln. By the way, in case you're thinking, oh, can't we just write that as ln of secant times ln of tangent? No, no, no. It doesn't work that way. So we have reached the end of our video, and we are going to save that final formula. Yeah, too many equals. Okay, there we go. So we have 2 important formulas. I will be reminding you of those in the next couple of videos. Integral for secant, ln of secant plus tangent, but for secant cube, it's a little bit more complicated. But this thing is inside that formula. All right, so thank you so much for watching our video for today. I hope you found that helpful. Until next time, I hope you enjoy the rest of your day. Bye.